In modern spaceflight, raw power no longer guarantees market dominance. To lead this industry, a rocket must be capable of returning to Earth for rapid reuse. Bringing a small rocket back to the pad is an engineering feat. Scaling that capability up to a heavy lift vehicle is a different class of problem, requiring a machine that can drop like a skyscraper from the edge of space and balance perfectly on a barge. Blue Origin designed New Glenn to solve this specific intersection of scale and physics, seen here standing ready at Launch Complex 36. The sheer size of the vehicle is staggering. At 98 meters tall, it towers over the landscape, standing nearly 300 feet higher than a standard Falcon 9. That massive frame supports a 7-meter payload fairing. Its internal volume is cavernous enough to fit 3 full-size school buses parked side by side. This capacity is built for the next generation of massive infrastructure, like the Bluebird 7 satellite, which deploys a communication antenna covering 2,400 square feet. But while this size solves the problem of massive payloads, it creates a new engineering roadblock. The more mass you put into the sky, the more energy you have to manage when you try to bring it back in one piece. Lifting a vehicle of this magnitude requires overwhelming force. At liftoff, New Glenn must generate 3.85 million pounds of thrust. This lift comes from a cluster of 7 BE-4 engines at the base of the booster. Traditional rockets rely on kerosene-based fuels that leave behind a thick, damaging layer of carbon soot deep inside the engine's internal piping. This buildup is the enemy of rapid reusability. It often requires engineers to spend months meticulously tearing down and cleaning engines before they are safe to fly again. To solve this, Blue Origin replaced kerosene with a mixture of liquefied natural gas and liquid oxygen, a combination known as Methylax. Methylax provides a distinct physical advantage. As this comparison shows, it burns completely clean, leaving zero particulate residue behind to clog the machinery. This clean-burning chemistry allows a single booster to survive a 25-flight lifespan without the need for extensive, time-consuming engine overhauls. These design choices faced their most significant test to date during the NG-3 mission. The booster for this flight, GS-1, was a veteran core that had flown before. However, it was launching with a fresh set of engines and updated guidance software. Beyond the challenges of navigation, the booster must survive a lethal thermodynamic hurdle, the friction of atmospheric re-entry that threatens to melt the returning machine. To survive this environment, engineers refurbished the thermal protection system at the base of the rocket to better shield the hardware from superheated plasma. These targeted upgrades, the clean engines, the refined guidance, and the thermal shielding, are what transform New Glenn into a functioning architecture of reusability. On the morning of April 19th, all that engineering was compressed into the final seconds of a countdown at Launch Complex 36. The ignition of the 7 BE-4 engines produced the characteristic blue-white glow of high-efficiency Methylax combustion. The 322-foot behemoth shook the pad as it fought against gravity, pushing into the Florida sky. Successfully clearing the towers proved the raw mass-to-thrust physics of the design were sound. But success at the launch pad only addresses the start of Blue Origin's broader mission goals. Minutes after liftoff, the stages separated. The upper stage continued toward orbit, while the first stage began its long, unpowered fall back toward the Atlantic. This trajectory requires the booster to survive a fiery descent, while autonomously pinpointing the drone ship Jaclyn, a tiny target waiting hundreds of miles away in the ocean. As New Glenn disappeared into the cloud deck, the mission became a waiting game. Whether the thermal upgrades would hold and the guidance system could land this 7-meter giant remained a high-altitude cliffhanger. About 3.5 minutes after liftoff, the New Glenn rocket separates. The upper stage continues its burn to push the payload into orbit, but our focus shifts to the 322-foot first stage, known as GS-1, as it begins its descent back to Earth. It's a massive cylinder of aluminum and steel dropping tail first into the upper atmosphere. No engines are firing yet. It is completely unpowered, plummeting through dark, high-altitude winds. This was the reality on April 19, 2026, during the NG-3 mission. This specific vehicle made history because Blue Origin was launching previously flown hardware into space for the very first time. Surviving the trip back down is a massive physics problem. If the descent angle is off by even a fraction of a degree, aerodynamic stress will rip the hull apart, or the friction of re-entry will simply melt it. Pushing a satellite into orbit requires raw power. Bringing a massive piece of hardware back intact is the actual test that dictates whether cheap, reliable spaceflight is possible. For GS-1, the destination was the drone ship Jaclyn, waiting far out in the churning Atlantic Ocean. Unlike standard rocket recoveries, the Jaclyn wasn't anchored in place. As the rocket fell, the ship was actively motoring forward. This visualization shows why. A stationary barge gets tossed around by ocean swells, creating an unpredictable landing angle. But a moving ship slices through the water. That forward momentum creates a highly stabilized flat deck. To make this work, the flight computers have to guide a 30-story building falling from space through crosswinds and plant it precisely onto a platform cruising through the open ocean. As the booster drops deeper into the atmosphere, the air thickens and aerodynamic friction starts to build up to extreme levels. Engineers refurbished the thermal protection system on the base specifically for this phase. This heat shield acts like an anvil, absorbing and deflecting the extreme temperatures of re-entry away from the delicate engine components above it. While the base deflects heat, 4 massive aerofins deploy near the top. By tilting these surfaces against the rushing air, the flight computers physically steer the falling structure through unpredictable atmospheric crosswinds. During this phase, the 322-foot booster functions as a highly precise heavy metal glider, fighting for control as it descends through the atmosphere. Then, just above the ocean, the BE-4 Methylax engines roar back to life, aggressively slamming the brakes to kill the booster's terminal velocity. This diagram tracks the real-time math of the guidance system. It has to perfectly match the rocket's downward speed with the Jaclyn's forward horizontal velocity across the water. The booster essentially pauses over the water, holding its vertical position as the moving drone ship slides directly underneath the exhaust plume. The massive landing legs swing outward. The booster connects with the deck, and mission control erupts as they confirm the survival of GS-1. When those legs locked into place, Blue Origin proved their massive, reusable hardware architecture actually works in the real world. As the smoke cleared on the Jaclyn, that single intact rocket validated the company's design goal, building a booster capable of flying at least 25 times. This chart maps the economics of reuse. Discard a rocket in the ocean, and you pay full price every time. But divide that initial cost across 25 missions, and the aerospace cost structure collapses. Reusing the first stage drops orbital access prices by 90%. The successful recovery of NG-3 signals a shift where orbital spaceflight moves beyond the reach of massive government budgets. It is now open for commercial business. That drop in price directly impacts NASA's immediate roadmap for the Artemis program. New Glenn's heavy lift capacity is required to launch the massive Blue Moon lander, providing the physical bridge needed to ferry astronauts back to the moon. Closer to home, these high-frequency, low-cost flights will supply the necessary heavy lifting to construct the Orbital Reef commercial space station. Returning GS-1 to the deck of the Jaclyn provides a reusable heavy lift platform, ready to support the next missions to the lunar surface.